So the result here is photons can be counted. This is a particle property. Experimental facts about photons. Photons have no mass. No means zero numerically, all right? So that means mass of photon is zero. They have no electric charge. But they do have linear momenta. Do have linear momentum. Given by magnitude of the photon linear momentum is related to its wavelength by this simple relation. Remember, wavelength of any wave, including the light wave, is known. So h is the Planck's constant. I forgot to give you. Planck's constant is in SI units. It's a universal constant. This means that light can be used in collision experiment. So just like these are two normal, ordinary particles. When they collide, momentum is transferred from one particle to the other one. Similar experiment can be done using light with a normal particles, such as electrons. And this relationship is obtained using such experiments. The name of the famous experiment is Compton effect. This is about collision of photons with electrons. So left side photons, that's about light, wave. The right side, electron. Electrons are normal particles. And through this, in this experiment, the Compton experiment, it is observed experimentally that momentum is transferred from the light to the electrons. What does it mean? If this is an electron, you shine light, and then either the direction of the motion changes as a result of collision, or its speed changes, or both will change. And this is experimentally verified. That way, this relation has been obtained, that magnitude of the photon is given by Planck's constant divided by wavelength of the light. Okay, so far we have discussed some new ideas, new facts about light waves. Now we turn to the particles. Now, what's a very important property of waves, according to classical ideas? Diffraction. Experiments have been designed, diffraction experiments. You have a metal surface, for example, and then you have a source to carry out the diffraction. Instead of light, electrons have been used. And it turns out diffraction occurs when you use electrons also. In addition to electrons, neutrons have been used, and again, diffraction phenomena is observed. In fact, even atoms can be used for diffraction, and diffraction is observed. This means that it's a standard wave property, diffraction. That means wavelength, right? So, from such diffraction experiments, a wavelength can be assigned to a particle, such as electron or neutron or proton or helium atoms. And it fits this expression. Planck's constant divided by magnitude of momentum. Of course, P is for a particle. Mass of the particle times speed of the particle. Please note, these two expressions are identical if you use the symbol P. All right? You just turn this around, lambda equals h over p. But the way the input is different in using these two expressions. To find the momentum of a photon, input is wavelength. There is no, because mass is 0 for a photon. There is no such thing as m times v. You just use the wavelength, and then you get linear momentum. In the case of particles, particles do have a mass, and their speed is available. So you use this expression, mass of the particle times speed of the particle, and you divide h into this quantity to get the wavelength of the particle. This expression is called de Broglie wavelength. Of a particle. Electron diffraction is used in modern day instruments, especially in there are instruments called electron microscopes. There are two types of such microscopes. One is called scanning electron microscope, short for another type is called tunneling electron microscope. But these electron microscopes are quite important instruments because you may see sizes of the order of nanometers. There is a central laboratory in our in this campus, and these instruments are available. All right, let us. So far, we have just done theoretical discussion. Let us give some numerical examples. One example is exercise 1. We have a 35-watt sodium lamp. Producing yellow light. With lambda equals 589.3 nanometer. There are such lamps, sodium lamps, and they produce yellow light, and the light is nearly monochromatic, which means all the light which is emitted by the lamp has the same frequency, 589.3 nanometers. The question is, number of photons emitted in 1 second. All right. Now, watt is a power unit. It indicates the total energy emitted by the source. The source in this case is sodium lamp, in all directions, the total, and in 1 second. So its unit is joule per second. Total energy, which means this light bulb emits a total energy in 1 second. (35 joules). So the question here is asking us how many photons are present in this much light energy. This is the total, all right? So, because each photon has using the wavelength, we obtain the frequency, and then from h times frequency, we obtain the photon energy. Photon energy is 33.73 times 10 to the minus 20 joule. This is the energy of just one photon. This is the total. Here we have n times. So from this is also joule, of course. 35 divided by this number gives us 1.038 times 10 to the 20 photons. The unit should be photons per second, because we have calculated how many photons are present in the energy which is emitted in just 1 second. If the time were longer, then more photons would have been emitted. Please note that number of photons is very large, 10 to the 20. Compare this with Avogadro's number. What is Avogadro's number? 10 to the 23. This is normal that number of photons is so much, near Avogadro's number. In fact, it must be this large, otherwise it would be very difficult to observe or count the number of photons. So in the macroscopic world we are living, the number of such tiny quantities is quite large. Okay, let us have an example about wavelength of a particle. Kinetic energy of electron this is the kinetic energy, average kinetic energy of electron in the ground state of hydrogen atom. Ground state of hydrogen atom. Hydrogen has just one electron, as you know, hydrogen atom. So the average kinetic energy is this much. Electron volt unit, let us write here. 1 electron volt is 1.602 times 10 to the minus 19 joule. Okay. Notice that this factor, this value, 1.602 times 10 to the minus 19, is the magnitude of the charge on the electron in coulombs. And in fact, this symbol, E times V, read it like that. Electron volt, but also E times V. For V, you have 1 volt. 1 volt. For E, magnitude of charge on the electron, which is this number. Coulomb times volt is energy. It is joule. All right. So using this conversion factor, this is joule. When you do calculations which contain different units initially, you should always convert them to a consistent set of units. In this case, SI units are very useful. So, because from kinetic energy, I want to calculate the speed of the electron. Kinetic energy is 1/2 mass times v square. In this case, mass is mass of the electron. Here what I'm trying to, here the question is this. What is the de Broglie wavelength of the electron in the ground state of the hydrogen atom? To find the wavelength, de Broglie wavelength, I need speed of the electron. But the information is, initial information is, kinetic energy is given to us. Using this expression, I can obtain speed of the electron. Of course, I need mass of the electron. I just look it up. Mass of the electron is 9.109 times 10 to the minus 31 kilogram. From this information, and so using this expression, mass of electron is given, kinetic energy is given here, here it is. So I can obtain v square and then take the square root to get v of the electron. So for the speed of the electron here, calculation gives 2.19 times 10 to the 6 meters per second. Now that I know the speed, this is known. This is mass of electron here. It is also known. H is known, so I obtain lambda for the electron, and the result is 0.33 nanometer. Uh, 0.33 nanometers means 3.3 angstrom, isn't it? 1 angstrom is 10 to the minus 10. Nanometer is 10 to the minus 9. Such a value for the wavelength corresponds to X-ray region in normal light, X-ray. And please remember that diffraction experiments are done using X-rays. So, whether you use an X-ray or electrons like with such properties, you obtain similar diffraction pattern. All right. Now let us go into more detail about interaction of photons or light with normal particles. So our title is Energy Exchange. Between light and particles. On one side we have light, on the other side we have a sample. Let's say composed of A atoms. This is a beam of monochromatic light at frequency or with frequency nu. As we have mentioned, the beam is considered as a collection of photons. Photons, let us use these are photons. All of them are moving in parallel to each other and in the same direction as the direction of the light. Okay. Now, there are n photons in the beam. N is very large. N is about Avogadro's number. We have just seen an example. Now, in the sample, we are assuming the substance is in the gas phase. These particles could be atoms or molecules. Okay. Now, the photons will pass through the sample, and then there is a detector on the other side of the sample, of course an instrument. This detector is counting the number of photons which have emerged. If the number which have come out of the sample is the same as the initial value, then no energy has been transferred from the light beam to the sample. However, if number of photons is less here than the initial, what does it tell us? Some energy, the light source, the light beam has lost energy. Where does this energy go to? It goes to the sample. So the idea is very simple. There are instruments which can do this. They can, at each frequency, they can count how many photons are coming out of the sample. Now imagine there is a light source here, of course. The light source is such that you may adjust the frequency of light which is going to be emitted, which is going to be produced. All right? And this is done automatically. You have an arrangement which slowly changes the frequency of the light. So this way, just imagine, as the frequency is changing by the light source, this instrument is counting whether number of photons which emerge, which pass through the sample are the same or different than the initial. And this way, for some frequencies, of the light, the number of photons does not change. That means no photons have been absorbed. But at some critical values of the frequency, it turns out that number of photons which come out here, let us say n prime photons. If n prime is less than n, that tells us that some of the photons have been absorbed by the molecules in the sample. Now, how does this absorption take place? There are very many photons which are coming, but also there are very many particles inside the sample. Just what is 1 mole? 10 to the 23, isn't it? So any sample will contain nearly Avogadro's number of particles in it. If you take one of them, say this one, if a photon, if this n prime number of photons is less than the initial, that means photons have disappeared. And its energy must be absorbed, taken by the molecules in the sample. Now, this energy exchange is a one-to-one exchange. What does it mean? One photon, say this photon, if it hits this A atom, the photon energy is transferred to the A, but there are other photons which are coming. The probability of another photon to hit the same particle is extremely small. So it doesn't happen. What does it mean? It means that one photon interacts with just one atom in the sample. So we use a chemical notation to indicate this. The photon is indicated by its energy, h times nu. One of these particles in the sample is indicated by the chemical symbol A. And if this photon is absorbed by the particle, then the energy of the particle increases. We indicate it by a star. So this is the normal A. This is the energized, more energy. Why? Because the photon energy is completely transferred to A. This transfer is not partial. In other words, it is not possible that half of the photon energy is transferred to the particle. It is either yes or no type problem. Either all of it will be transferred or none of it will be transferred. If none is transferred, the number n prime will be the same as n here. But okay. So now if we indicate the energy of the normal particle by EI, initial energy, this is the final energy of the same particle, then energy conservation tells us that photon energy plus initial energy, this is the total energy initially, must be same as total energy finally. But the total final energy is just final energy of the particle. So we can rearrange this as and write it E final minus E initial, or just delta E, energy change in the particle. Please remember this fact. The left side, h times nu, is about photon, about light. The right side, E final minus E initial, or delta E, is not about light. What is it about? About the particle. Don't forget this. To know delta E, we have to know initial energy and final energy of the particle. Only if the photon energy is the same as for the particle, E final minus E initial, only then photon will be absorbed. Otherwise, it's not going to be absorbed. It will just go through. All right, let us expand this concept. Now we are going to discuss possible values for the initial and final energy of a particle. So we are discussing energy levels of a given particle. Energy levels. I have used here material particle to make a difference between, for example, light. We just said light also has particle properties, right? By material particle, I mean normal particles, or the classical particles, all right? Electron, atom, neutron, proton, molecule, those are our particles. Now, very many experiments through the centuries, people have carried out millions or maybe billions of experiments on such properties. And it turns out that any particle will have certain energy levels, and only at those energy levels the particles are stable, have some stability. And so, qualitatively, if this is increasing energy, there is a minimum energy, which is called, say, or I will give the numbering later, but the allowed energies look like this. These are allowed. Notice that, well, each dash means a certain value for the energy. The energies are, they are not changing continuously, but they are jumping from one value to another one. Say from this value to that value, to that value, to that value. The experiments show that any particle that you take have such a behavior as far as the stable energy levels are concerned. These energy levels are numbered, starting with the lowest. This is the lowest allowed energy. every particle has one energy which is lowest in value. That means there are no lower energies. That's one thing. This lowest value for the energy is called the ground energy level. Ground energy level. Now, let us number them. I will number the energies starting with the lowest. Lowest is 1, 2, 3, 4, and so on. And sometimes the numbering starts with 0. All right? Sometimes the ground level is given 0, and then 0, 1, 2, 3. It goes on like that. But here, for this purpose, I will start with 1. So I will write this is value E1. In fact, here, this value is E1. This value is E2. This is E3. This is E4. And so here we are indicating by symbols the possible energy levels of the particle. Repeating the lowest one, the lowest value is called ground energy level. All the other higher energies are called excited. So these are excited energy levels. Therefore, the full set of energy levels is classified into 2 types. One type is just one value for the energy. That energy level is called ground energy level. All the rest of the energy levels together are called excited energy levels. Now, even though there is a limitation for the minimum, for the lowest level, there is no limitation for the upper. The upper value, it may go up to infinity. Okay? Later, when we discuss the photoelectric effect, I will give another diagram to you. The general behavior of the energy levels is as follows. Energy levels which are near to the ground level are discrete, which means discrete is the opposite of continuous. If numbers are jumping from one value to, say, from 1 to, first number is, say, 1, second number is 5, and no 2, 3 available, jumping directly from 1 to 5. Such non-continuous change in values is called discrete. So these are discrete values, or we use the word quantized. Quantized energy levels means numerical values are discrete. Near the ground energy level, say in this region, the energy levels are discrete, but if you go to very high energies, then the energy spacing between energy levels become smaller and smaller and smaller, such that after some point, energies change continuously. That part is called the continuum energy levels, and the lower part is called the quantized energy values. In most of our experiments regarding such properties, the quantized part is the important one for us. Spectroscopy, infrared spectroscopy, UV spectroscopy, microwave spectroscopy, all of them are based upon the quantized or discrete part of the energy levels. Now, coming back here, if that energy level diagram is indicating just one of these, the allowed energies of just one of these atom or molecule here. Both of these numbers, initial and final, must be one of these values. You cannot just arbitrarily take a value. It has to be, there are two values, one of them. Suppose we, let us imagine initially, all of the A molecules in the sample are in the ground energy level, which means we know initially all have the same energy, this energy. Here, this one. Then, what are the possibilities for final? Either this value or that value or that value. So, this chemical expression here, describing absorption of photon, is indicated in a diagram of this type by such a drawing an arrow from the initial level to the final level, if the final level is this value. So it is indicating a transition from the lower energy level to the higher energy level. What must be the frequency of the photon which will cause this transition? These are known. The frequency must be equal to the difference, E2 minus E1. All right? Now, as we said in the experiment, the light source is monitored. It is changing the frequencies. So, when we scan the frequencies, we will find that other frequency of photons will also be absorbed by the sample. What is the next possibility? This is a possibility. Now, for this transition, we need a larger frequency photon, isn't it? We have E3 minus E1. Now, so let us number the photons also. 1, 2, like this, in increasing order of the values. Here is a lower frequency photon, and we can obtain the value of frequency if we know E2 and E1. This is a larger frequency photon, and if we know the numerical values of E3, we can obtain this. And this way, depending on the frequency of the photon, there are many possibilities, of course. This is also another possibility. You should also remember this. There are extremely many photons. We said that of the order of Avogadro's number, 10 to the 20, 10 to the 21, 23 photons. Also, number of atoms or molecules in the sample is very large. So, photons of this frequency, which cause transition from the ground to the first excited state, can be absorbed by many different atoms in the sample, but let us say 5% of the atoms absorb the first frequency of photons here. The remaining 95% are in their ground states. Those, when we change the frequency here, the source is changing the frequency. The second frequency, for instance, that nu2, will be absorbed by some of the remaining 95%. In other words, different photons are not absorbed by the same atoms. They are always absorbed by different, because the sample contains so much substance. However, we use the same diagram to describe all these different absorption processes. Why? Because the atoms or molecules in the sample are all identical. All have the same set of allowed energy levels. So the first frequency, say, by these molecules, the second frequency by some of the other molecules. And then, as we change the frequency, other photons will could be absorbed, because this doesn't stop. Here we have others, E5, E6, and so on. So such transitions are also possible, and they will be observed in the experiment. Okay, our time is up, so let us stop here.